אז היי, שבת שלום לכולם, אני נועם, כיף להיות פה, האמת שזה נורא מוזר לי שזה פנים, זה נורא כיף, כאילו כבר ממש התרגלנו, אני מניח שאתם כבר התרגלתם לחזור לכיתה, אבל ממש כיף לראות אתכם, תודה שהזמנתם אותי ונתחיל. אז קודם כל אני אציג את עצמי במילה אחת, תגידו לי אם לא שומעים או משהו במיטאפ שם, אנחנו נתחיל. Okay, we'll switch to English. The talk will gonna be in English. I just allowed myself to say hello in my native language, but will be good in English. Yes, we good to go? Great. Okay, so hi, I'm Noam. Let me introduce myself quickly. So I'm in the last 3 years doing product management for Viz.ai. From being a very small startup with high ambitions to what you're going to soon see that Viz is today. My focus at Viz is working with our AI group, developing clinical products that are based on AI that we clear and we serve patients with. On previous lives, I was in the education industry working in a startup called Ingicell that was acquired by Cisco, doing algorithm development, leading a team there, and then moving to product management, which is what I'm doing for the last few years. And if you go even way before that, my academic background is from Ben Gurion. I studied electrical engineering and physics, but that goes way back. A few of the things that I love, so I was born and raised in Tel Aviv. I love the city and I love the beach. I'm married to Daniela that owns the fashion brand Sisters that I hope some of you know already. And we're trying to raise 2 city kids, as you can see down below. So that's me. So what we do today, the session today will have 2 parts. In the first part, we're going to talk a little bit about Viz.ai, what we're doing and the mission of Viz.ai. As you can see, the mission for us at Viz is synchronizing care to improve access to life-saving treatments, and that's what we're doing, or at least trying to do at Viz. And in the second part, we'll dive a little bit deeper into one of our products. It's called CT Perfusion. And we'll talk about real-world challenges developing a stroke perfusion analysis algorithm. So in the first part, you'll hear a little bit about Viz, and the second part is going to be a little bit more technical. Can you hear me okay in the Zoom? I feel like I'm cutting in and out.
Yes.
Okay. All right. So before we dive in, I have one request for you guys that you will see in just a second. Please do ask questions. Please interrupt me. Please just ask whatever you're interested in. The purpose of me being here is you. Okay, I'm not here for myself. If I'm talking for 60 minutes, it might be boring. Please do ask questions, interrupt me. If you're on the Zoom, either in the meetup or in the class, please text the questions to Miriam, and she will ask me intermediately. All right, good to go. So let's go. The first part, we'll talk a little bit about Viz, and I'm going to start from the very beginning. So Viz's focus in the early days was stroke, and I want to start from the basic and explain a little bit about what is stroke. So stroke, most of the stroke, what we call ischemic strokes, are when clot travels the body back in the brain. When the clot is stuck in a vessel in the brain, there's no blood flow to the brain. When the brain cells don't get blood, they die like any other cells. But other than other cells in the body, when they don't get blood, they don't get oxygen, they die, and there's no way to replace them. So any brain tissue that is dead forever. That's why stroke is so time critical. Few facts that you might know already. Stroke is the number 5 killer in the US. It's number 3 in Israel, actually. There's almost 1 million Americans that suffer stroke every year. It's about 20,000 in Israel. It's the number 1 cause of disability in the US, and I think that in Israel as well. And about 1/3 of stroke patients actually die from the stroke. Another 1/3 get permanent disability. It's a devastating disease. It's a huge burden on families, on the health system, and on society as a whole. So that is, what do we do? Starting in 2015, there's a new treatment that we call mechanical thrombectomy. That's magical, really. It's one of the most effective and efficient treatment in medicine as a whole. What we do is that if a person, as you can see, or maybe you can see, has a clot here in one of the main blood vessels in the brain, what we do is that we put a small hole in the groin and we travel all the way across the body with a plastic catheter. We go out to the head and we get near that clot, sucking it out or pulling it out. There's very fancy devices. There's a lot of high tech in there as well. Pulling the clot out, taking the tube out of the body, and in many times the person just walks away from the hospital. It's highly, highly effective, very, very minimally invasive. So you just go travel through the veins. There's usually no damage to the body at all. That's meant to save people after they got stroke. So if you did unfortunately have a stroke, you have a clot, blood clot stuck in the brain, and the way to save the patient is actually to remove the clot, and that's the way to do it. Yes, it's צנתור מוח בעברית. Okay, so it's similar to surgery that we used to do in the heart, like צנתור לב, but just in the brain. And it's rather new. It's only since 2015 it got into the guideline, became widely available, but it's effective and it works and it's magical. And I've seen patients that can't move. You pull the clot out, blood perfuses the brain, they just stand up and walk. For minutes to, I mean, if it's easy, it's minutes. The question was how long is the operation? So if it's easy, it's minutes. You can go up, pull it out, even 10-15 minutes. If it complicates, it can go to an hour, depending on how complex the case is, but it could be minutes. Yeah, so the question, if are there cases with multiple clots, and the answer is yes. Many times people have a small, like a big clot here and then small clots on other places, and there are complicated or complex operations that you go in and you pull multiple clots out. So yes, that's actually frequent. That is correct. We first do a CT, and I'll talk about that in a minute. Cool. So we have this new and fancy and effective treatment, but what's the challenge here? The challenge is time, and that's the title of my talk today. Time is brain. Why? Because every minute that a stroke patient doesn't get treatment, 2 million neurons die. Every minute equals a week of healthy life, and about $1,000 if you try to think of how much it costs to a hospital. The burden to the family is obviously, and to the patient is huge, but if you try to quantify, and there was research trying to quantify how much a minute costs, so a minute is a week of healthy life, and that's just some numbers to get a sense of it. But the tragedy here that only 50% of patients actually get the appropriate and the timely treatment. Any thoughts of why? One by one, sorry. It takes time to get to the hospital. What do you mean? It takes time to find and understand that actually it's a patient you can treat. So it takes a long time to take the imaging that we just see and take it to a doctor. Yes, it is expensive to do a CT, but actually stroke patients usually do get CT and even pretty quickly. That's actually a very good point. Sometimes strokes doesn't appear as stroke. It kind of stroke. There are strokes that look like the person is drunk. Sometimes the person is just fainted. So it's not always easy to see. I'm sorry? Where the location of the clot is? Yeah, so some clots are harder to get to and they're hard to get to. Everything you said is actually right, and we'll go through it in 1 second. If I want to summarize everything that we just said in one word, this word is workflow. And workflow is everything that happens to a patient since the moment they get a stroke until they're treated. So let's go through the workflow very quickly, and you see that all the answers that you just gave are actually very accurate. So if a patient gets a stroke, they call 911. They're driven to the hospital, usually very fast. They get evaluated in the ED, Cheder Miyun, emergency department. They get CT scanned. Someone asked before, that actually happens pretty quickly in most places, because if a stroke has distinct symptoms, the first thing you do, you put a person in the CT. They go back to ED, but then the scans are sent to radiology. So we need a radiologist, a neuroradiologist, to actually go through the scans and see what's inside. If the neuroradiologist sees that there is something in the scan, They send the patient back to the ED and then they call neurology. So we need to bring a neurologist to the ED to examine the patient. He does a neurologic exam, usually takes a few minutes, and checks what happens with the patient, what's the clinical situation other than the CT. And if he thinks there's something to do, then he calls an expert. He calls a neurosurgeon, an interventionalist. You know how many of those we have in Israel that can do mechanical thrombectomy? Guess? About 13. I think it's 14 now. Okay, I think there's 9 hospitals and 14 surgeons in Israel that can do the treatment. We need to get the images to the surgeon. Someone said it before. Even in 2021, getting a CT scan to someone that is not in the hospital is not trivial, and it takes time. They need to coordinate the transport. Many times transfer the patient again from a small hospital to a bigger hospital and treat. And I'm not sure about the ratio. The problem is Israel mainly is the inequality of care. Yes, of care in Israel. So if you live southern than Ashdod, I think there's 1 neurosurgeon, and if you live northern than Hedera, there's 4. So we were implemented in Israel, and we will be implemented in Israel further in the future. Okay, how long do you think that takes usually? Best case scenario? Best case scenario, very good hospital, 1 hour, 2 hours, 3 hours more. Okay, so your ballpark is right. In very good hospitals in the States, it should take around 2 hours end to end, which is fast. 2 hours for all this process is very, very, very fast. Unfortunately, in many places, if you get to, again, peripheral or other places, it can take longer than. So what did we do with Viz? We came up with what we like to call synchronized workflow. So once a patient gets into the CT scanner, we send the images to the cloud, we analyze them with AI, and then we trigger action. What do you mean trigger action? We send a notification to everybody here. All the parties that are involved in stroke care, they get a notification on a mobile app. They can view the images very quickly, chat in a secure way, decide on treatment, and get the patient to care early. And that's the idea of Viz, and that's what we're trying to do. When we launched the stroke package, we launched 4 products. The first is LVO, which is an algorithm that can detect large vessel occlusion. So we get a CT scan, we process it with AI, and then we say, yes, there's a large vessel occlusion. No, there's no large vessel occlusion. Large vessel occlusion is the type of stroke that you usually can treat. So it's a big vessel with a big clot that can be pulled out. We have CT Perfusion. It's actually we'll discuss in the second part of today. And Viz.ai, which is a mobile image viewer, that you'll be surprised to hear how much of an impact the sole ability to actually view images on the mobile, on the go, and not in the hospital is huge for physicians in many places, and a communication tool. So that's the package. So that's a good question. We're not replacing nobody. We're a parallel pathway. What we have to do is to get the right patient to the right doctor in the right time. So we want to have this neuroradiologist or neurosurgeon that can make a decision, see the images fast. We want to enable them to ask questions and get the clinical picture fast and make a decision. I beg your pardon. Okay, so what Viz.ai does is actually provides a yes/no classification. So if there's a standard we think that has a large vessel occlusion, we shoot out an alert, and if not, then we don't provide specifics. CTP, which we'll cover later today, is a more specific analysis tool to get more details about the actual of what's going on in the. So again, the leftmost, I'll explain again, the leftmost Viz.ai is detecting large vessel occlusion. So we get a scan, we say, yes, there is a stroke. We notify everybody. No, there isn't. We don't do anything. Second one is CTP, we'll touch on later. The third is just an image viewer, just viewing the images in the mobile app quickly and efficiently. Scroll through. It's a mobile CT viewer. There are mobile CT viewers out there, but we argue that ours is the best, and it's actually very useful and very quick. And then the last one is just communication. Yeah, so it's a similar question. The question was what happens if we don't find a stroke? And the answer is that we are what we call a parallel pathway, so we don't replace the doctor. So every image is going to be reviewed by the radiologist anyway. But there's a good chance that if we did find something, we're going to push the person up the line and get to the right physician in the end of the queue and save the patient of going into all those steps that will take time. They will happen anyway, but it just take a lot of time. That's a good point. The question was if doctors fix us sometimes. Yes, we make mistakes. There's no perfect algorithm out there. We'll talk about it a little bit later. Yes, the question if we use data or labeling by physicians for retraining the algorithm. So yes, we have a team in-house that does labeling, and we also use feedback that we get from customers. Great question. The question was if we're using other data other than the CT scan in determining if that's a stroke or not. The answer is no. Because of the nature of the product, we get a CT scan, we analyze it, and we give the result because we don't always have additional information. It's anonymous, and then there is a chance. I mean, there is a chance. It's probable that if we do add information, we'll be better. But that's what I want to move forward just a little bit, so we cover more things today. But thank you for interrupting, and please keep on asking questions. I'm going to go quickly with what we did in Viz since 2018 when we got the first clearance for Viz.ai and Viz CTP. This is a press release by the FDA, actually. What we did in 2018 was create a new category for FDA, which is called computer-aided triage. So those are systems that are helping physicians to make decisions that receive a CT scan or an MR scan or what have you, and provide a yes/no answer. Yes, there is a stroke. No, there isn't stroke. Today, there's a lot of products in that category, and we're proud to be the first, and we're proud to have competition now. But this is also applied in other states, not only stroke today. In 2019, we started rolling out the system nationwide in the US. And when we started rolling it out, we managed to prove that we're not just telling a nice story about how Viz can save lives, but we actually are making an impact. And I'll give a few examples. Example one is from a hospital in Texas, very south in Texas, a big stroke center, that they managed to show that pre-post Viz, they've saved almost an hour with transferring patients from a smaller hospital to a larger hospital. Another big system in Denver, which called Swedish, HCL Swedish, they have proved or tested and demonstrated that they've managed to get more people to treatment than they used to get people to treatment before this because of the time saving. And most importantly of all, this is a study out of Mount Sinai in New York when they've proved that we actually impact outcomes. Outcomes is what happens to the patient after they leave the hospital. If you can see this orange box over there, so they managed to show statistically that we managed to improve a score that we call 90-day MRS from 5 to 3. MRS is a score from 0 to 6. 0 is a healthy person. 6 is a dead person. So between healthy and dead, there's a short scale. And they've managed to show that we managed to this average of 5, which means that many stroke patients get out of the hospital or die or have severe disability in 90 days to 3. In 2020, we submitted the data, all the data that we collected to CMS. CMS is the government insurer in the US. So if you don't have a private insurance, if you're old or if you're poor, you get insured by the government, and they issued what they call NTAP. NTAP is new technology add-on payment. It's a payment that they provide. They give the hospital money. They pay the hospital to use the software in order to encourage the use of new technologies. So that means that for every patient that's on Medicare or Medicaid in the US, if they go to the hospital and if the scan is analyzed by Viz, no matter if it's a stroke or not, they'll get reimbursed. They can get a check of $1,000. That's how much we managed to convince it's effective, and that's a first for AI, for software that actually does something similar to what we do. Questions? HCA Swedish. Yes. Yes, so the next slide here, you will see that we're live in over 850 hospitals in the US, almost 1,000 hospitals now. It's a big portion of the US hospital system, big stroke centers in the US. We're starting now to implement in Europe. And for the question about Israel, we're hoping to be live in more places in Israel. We had some challenge. So the question is, what about third world countries? So taking a step back, the product that the software and the product that we make is a medical device, and it needs to be approved by the regulator. In the US, it's the FDA. In Europe, it's a CE mark. And in the world, there's different regulations, there's different rules, and there's different business environment. We started off with the US. We are going to Europe now, and we're hoping to be in more places later. That's a great question. The question was, do we need to implement a different system in different places? So we build the system in a way that it can adapt to the workflow that they're doing in the hospital. The tools that we provide are rather generic, and we find that different hospital systems use them slightly differently, but the concept is similar. What is different is that we go to different regulatory authorities. Then there are some limitations, some things that we can or cannot do. So the question was, how variable is the data between hospitals, between scanner manufacturers, between scanning techniques? And the answer is very, very much. So it's a challenge, and we'll get to it later in the talk. The question is if we integrate with other systems in the hospital. We have an integration that we're promoting with the EMR. It's the electronic medical record. That's something that we're doing, and mostly we're imaging based. So we integrate with the PACS in the sense that we get images and we send images, yes? So there's a lot. So the question. Yes. So the question was again about variability. There is variability in population. People's brains are different. The anatomy is different. Yeah. So now we're in enough places to have very variable data sets, and we are taking into account as much variability as we can. Still, we encounter a new manufacturer with a new scanner that has some challenges of performance, or for example, technicians that do the scans in one way or another that is not exactly what you're used to, but that's a challenge. And just to wrap up this first part, we are expanding. So we're expanding to new disease states. We just launched our pulmonary embolism detection, the tasrif reati, and aortic dissection detection, and we're moving into other disease states in the brain and other disease states in the body as a whole. We're moving to new modalities, so MRI, X-ray, other exciting things that are going to come, and we're expanding globally, as I mentioned before. So the question is, what do we do with pulmonary embolisms? And the notion is that pulmonary embolism is a less urgent disease than stroke, which is true. And what we believe is that if we manage, again, to find those PEs, those pulmonary embolism, in places or in times in the day when there's no resident vascular surgeon or there's no resident vascular expert radiologist, then we can promote people and get them care earlier. Of course, it's not as urgent, but again, mobile view and communication, early alerting is something that we believe is applicable there as well. Questions? Okay, we're good with time. Any other questions about Viz, about what we do, about the algorithm before we move on to the second part? Go ahead. I don't have a slide. The question was, how do we measure the algorithms? That's a good question. We use, I mean, for at least for LVO detection, it's a good example. We use the classic sensitivity and specificity, so precision or recall as the key measures. We're also looking at time, how much time it takes us to analyze the scan and get the result. We're looking at yield, so how many of the scans we manage to process, and on robustness of the system. So if there's any, software glitches, bugs, etc. So those are the 5 metrics that we usually judge ourselves by, sensitivity and specificity being, for detection being the most important and most common. The question is what happens with the false positive, or what's the question again? So a false positive by definition is when we alert and there's no last vessel occlusion. Sometimes we get the feedback, sometimes we don't, sometimes we don't even know that it happens, sometimes we annotate it internally and we improve, but that's a part of the system. No, so it's not fully automatic. The goal here, if we have plans, I mean, we're not, so the question is if we have a plan to be fully automatic or do the whole thing end to end. It's a hard question. Realistically, our mission is to get people to treatment faster, earlier, and to get them to the right doctors. It doesn't necessarily mean that we can perform the operation. That's not what you're trying to do. So that's what we're doing. If I'm sorry? Okay, so 2 questions. The first question was what's the algorithm based on, and we'll answer it in depth here for one of our algorithms. Some of them use neural network. Usually we use many things. So neural networks based machine learning, signal processing, depends on what we're doing. We'll touch on that in a second. And I'm not sure I follow the second question, but we have patients that suffer repeated strokes. It's sometimes harder for us to detect, but that's something that we deal with. The question was if, because the disease is severe, we try to optimize for sensitivity rather than specificity, and the answer is no. We try to balance sensitivity and specificity, because if you're very, very sensitive, you're less specific, and you're going to issue many alerts. You're going to wake up many doctors in the middle of the night, and they'll just stop using the system. So there's a balance. So I want to move forward with your permission. Last question. So the question is, what is the difference between us and competition that does similar things in terms of detection of strokes or other? There is competition. There's actually another Israeli company called AIDoc. There's a lot of companies out there the same. We believe that what we did is special because we're a workflow company. We're not an imaging company. We look at the workflow, and we're trying to solve for the workflow. Other companies might go to the radiology specifically or to the neurology specifically, depending on the settings, but we try to look at the workflow in a whole, and it works for us so far. So I want to move forward to the second part of today. We learned a little bit about stroke, we learned a little bit about the problem, and I want to describe in depth and walk you through one of the problems here and how did we solve it with our CT Perfusion product. So what's the problem? The question is, how can we measure risk versus benefit for treatment? We have a treatment, we know it's highly, highly effective, we know it's very, very, very time sensitive, and we need to make a decision fast. But every treatment has risks to it. If we get a patient in treatment and the clot is already old, most of the brain that could die already died, there's more risk in performing the operation than benefit. On the other hand, if there's a patient with a new stroke, with healthy brain, and we can pull up the clot and get a reperfusion, then we can save the patient. And it's a very hard question. It's a very hard decision to make for surgeons. And then the second question is, what if we had a way to predict how much brain will be saved? So if we want to make a decision yes, no about treatment, we need to know yes, no, will that patient benefit from treatment, or no, are you going to kill the patient by going into his brain and picking his vessels in the brain? It's a complex question, and science invented a way to try to help physicians answer it, and that way is called CT Perfusion. So CT Perfusion is an imaging technique to assess blood flow in the brain. Clinical thresholds are used to detect potentially salvageable brain tissue against probably dead brain tissue. Let's read it again slowly. We're looking at an image here, and we're trying to determine which parts of the brain are probably dead, what part of the tissue is probably unsalvageable and it's gone, and what part of the tissue here in green is probably salvageable, and perhaps we can save the patient. And according to the ratio and the difference, we know if whether or not we want to take the patient to treatment. So you can see that if the ratio is high and the difference is high, then we're more favorable for treatment. And there's clinical thresholds that are accepted and tested by clinical trials and literature. We're gonna play a little game here just to see that you get the point. You have two examples here, A and B. Show of hands if you think that patient A is in a favorable condition for mechanical thrombectomy. Show of hands if patient B is a good candidate. Great. I'll take the credit for explaining it easily. So you guys got it easily. So yes, if there's a small, what we call core infarct, dead brain, versus a large area of brain that's potentially salvageable, it's not for sure, what we call penumbra, then yes, we want to take the patient to treatment. How does it work? What is CT perfusion? How do we do that magic? So CT perfusion is a contrast-enhanced CT scan acquired over time and post-processed to analyze blood flow. Let's read it very slow and together, and I think we'll get what it is. So what does it mean, contrast-enhanced CT scan? We put the patient in the scanner, you inject a contrast, it's like a dye to the blood flow, the contrast flows in the brain, and then you take the scan, you take the image of the brain while contrast flows into the brain. So we time it together, we inject, we wait for contrast to get to the brain, we scan, and then we stop. And not only that, we acquire it over time. So what does it mean over time? We put the contrast in, and not only we scan once, we scan multiple times. So once contrast gets into the brain, we start scanning multiple times until it leaves, and we get a four-dimensional result. Four-dimensional because we have 3D volumes in time. So we have a few time points of 3D volumes, and in a minute you'll understand why am I doing this wave with my hand. But as contrast goes in, we scan, contrast goes out, we scan the brain, and eventually we post-process it with fancy signal processing tools to get this. And this is a map, similarly to the green and maps that you saw before, that allows physicians to learn about not only what part of the brain is dead, but which parts. So what parts in the brain, if this is the area that's responsible for motorics, if it's an area that's responsible for something else, then I can make a decision. That's a bit complex questions. I mean, to follow, it's important that we understand how it works. Here. So the question is, what are the 4 images? We'll get to it later. It's different parameters for blood flow. So it's the volume of blood flowing, the ratio of blood flowing, how long it takes to the blood to get to a certain point. We'll get there in a second. So scan without contrast looks like this. You see a lot, but you don't see the vessels. You see the tissue. So if you wanna, the first scan that the stroke patient gets is a non-contrast. You see the tissue, and if you wanna see the vessels, then you inject contrast, and you get something like this, like a negative, in a way. So we said, let's do it. So we have the inputs because we get them from our customers. We know how the output is supposed to look like. There's very, very well-published, well-researched literature that explain the math of how do you take this very complex 4-dimensional array and make those nice maps. So we said, okay, let's just implement the papers. And you can guess how it went. What challenges can you guess that we had with the data? We're processing the data. Variability in inputs, yes, that's a great point. The slides are intentionally not at the same time. So I'll take it to another way. The way that the technician is actually running the scan is very important for the scan to be coherent and for us to be able to understand it. So there's a lot of mastery in actually performing those scans. It's a complicated scan to perform. So the question, if the system exists and the algorithm exists, what are we trying to do? So what we try to do is actually clear with the FDA a product that can consume those images, do the post-processing, and do the processing, I mean the math. Do the processing and take raw images and send back analyzed images. Yes, the algorithms are well published, but if you want to use it in clinical practice, you need to go through the FDA. There's a few dozen companies that do it in the world. We didn't invent CTP in a way, but we want to implement it. And as you can see, there's challenges to it. So I'll take a step back. CT Perfusion is a type of scan that is performed in many places around the world. The way to get the input and construct the output is well known. It's not a trade secret. But if you want to create a product that actually does that, the post-processing, and serve real patients with the post-processing and give them maps so physician can make decisions, you need to go through FDA and you need to clear and build a product. Okay, so we went through some of the challenges. I want to go through a few examples for the challenges. And I've picked 3 main challenges, and you'll see why in a second. So challenge number 1 is that patients move. You put a stroke patient for 2 minutes in a scanner, you ask them to hold still, they breathe, they're sometimes panicked, they sometimes in seizures, sometimes they don't control themselves. This is how a good CT perfusion looks like, or a stable one. You can see that the contrast goes in and goes out. It's like the curve that I illustrated with my hand. And that's another example of a scan that's less easy to read. And you can imagine that if you want to try and take this into a deterministic post-processing algorithm, the results will be inaccurate in the good, in the better case, and embarrassing in the worst case, and it happens. Another challenge that we had is that there's more than just going to the CT scan. So the processing algorithm assume we're looking at brain tissue. There is skull, there's bones in the scan. Sometimes there's artifact. There's area in the brain that we don't want to analyze. We'll see in a minute. And we need to filter them out somehow. A third challenge will be choosing the right reference point. So I hope some of you are engineers or mathematicians. and you understand that there's no method we can do without a reference. And what do I mean by a reference point? This is the curve of contrast going in and out of the brain. We need to decide where do we start. So if we're looking at this map that looks for how long does it take for blood to get to the brain, this green part, it's blood that traveled for more than 6 seconds. 6 seconds since when? And we need to find a reference point, spatial reference point and temporal reference point. We need to find where in time it is and also where in the brain it makes sense. And those are 3 challenges that I want to review with you guys. I'm sorry. So breaking down the problem. So as I already told you, I'm a product manager. And if there's one thing product managers likes to do is break big problems to small problems. And this is what we excel at. And in this situation, again, we wanted to take this huge, very complex clinical problem and break it into engineering problem that we can solve. So try to define engineering problems with clear goals, engineering problems that has clear metrics, and try to optimize for the specific metrics in each case. And we came up with this pipeline, as you, I think, can understand, which is pretty straightforward. We correct for motion, we extract the soft matter, the brain, we choose a reference point, we do the core calculation, and then we post-process. And that's a very high level view of the pipeline of the algorithm. And what's important here is that for each step in the way, you need to choose the right tools for the job. Every step is different, the goal is different, the metric that you want to choose to optimize for is different. And the key here is to actually find the right methods, describe the problem well, model it to the right problem that we want to solve, and then solve it with the right tools. And I want to go through the 3 problems and see how did we do it. So first problem is a registration problem, which I think someone already mentioned. Okay, we want to register all volumes in all time points to T1. Take a minute to think. Any ideas how to solve such a problem from your experience, from your guess and imagination? That's an example. Maybe it's not a very drastic example, but as you can see in T2 here, the brain is shifted to the right, and then after this phase in the algorithm, the brain is registered to T1. So we need to create both a rotational transformation and also a translational transformation. And how did we do it? In this case, we actually did use deep learning. So we developed a neural network that does the registration. I'll give you a secret. We didn't have to. There are Python packages readily available that do exactly that, registration for medical images. We did choose to develop an in-house neural network that solves the problem. And the reason is time, because the packages that we had available were slow, and the neural network that we developed was very quick and very accurate and very useful for us. Next up is soft matter extraction. So the first problem here is to take out the bone. Any ideas how can you take this image on the left and remove the bone? Thresholding. I'm sorry? Edge detection. Other guesses? Sorry? That's a good point, actually. But to summarize everything you said, we're looking at image processing. So classic image processing techniques. Bone is very dense. The values, the attenuation in CT is very high. Brain is somewhere over here. Bone is somewhere over here. You can put a nice threshold, do some erosion, deletion, and it works. And that's it. And it worked. But what about the second case? You can see, taking a step backward, you see the black butterfly in the middle? So that's what we call ventricles. Ventricles are like holes inside the brain that have fluid in them, and that's the fluid that the brain floats in. And we need to remove them. Why do we need to remove them? Because they skew the results. There's no brain in there. We don't want to process them. How do we remove those? Any guess? Okay, trying to predict based on other brains that we see. Any other guesses? Image processing, it's black. The brain is not black. Maybe you can just put a threshold. Any other guess? The answer is that we actually eventually did use a neural network to do so. We did use image processing in the beginning. So when our data set was smaller and we're early in the days, we did use image processing techniques. But as we got more data from more places, variable data, people with very varied anatomies, different scanners, we find out that the threshold is not good enough. So we developed a deep learning technique. Another reason that we moved to deep learning for ventricles, but we didn't move for deep learning for the bones, is that if you make a mistake in the bone, it doesn't really matter because there's usually no, from the nature of the problem, most of you've seen in the maps before, most of the interesting parts are here in the middle, and it usually doesn't get here to the periphery. But the ventricles are super, super, super important because every mistake you do in the ventricles, if you over segment them or under segment, you actually change the decision for the physician. So if you take a ventricle into account, you add 10 cc to the volume, maybe the patient is not going to treatment. So that's why we chose it here and we didn't choose it here. Third problem, reference point selection. So I mentioned earlier that we want to find a reference point that is correct temporally, so it's in the right time, and also spatially. Eventually, we choose one point in the brain and compare everything to that point. And that point should be somewhere when contrast flows well, when the curve of the attenuation looks nice, and also somewhere that makes sense anatomically. Because if we find somewhere with a curve that looks nice, but it's somewhere over here, then it doesn't make sense because we want to try to compare blood that was before that, I mean temporally, to that point. So there's a complex problem here of choosing the right point, both in terms of anatomy in the brain and in terms of how the graph looks like. Any guesses? What would we do? What did we use? Neural network, it's one guess. Just guess. Comparison between the points, so ranking the points, yes. Trying to use more than one point. Image processing actually does work here. So we mentioned the image processing, you mentioned deep learning, you mentioned the machine learning or ranking. And to be honest, we use everything here. The question is to all. We use signal processing, not image processing, but signal processing to actually find places when the graphs look well. We rank the candidates based on features that we have in the image, using machine learning, using an SVM. And then last but not least, we use neural network to actually detect the vessels that make sense anatomically and add an anatomical prior into the mix. It's a complex problem, and we use a few tools to solve it. But I think the key here to understand is that after you think about the problem, in the end of the day, it's a ranking problem. Okay, so it's not a segmentation problem. It's not, I mean, one can think about it as a segmentation problem, as many types of problems. But in the end of the day, we want to rank and find which candidates are the best candidates. And we used pretty much everything to make it happen. Yeah, so if you look at each point or each voxel in 3D, there's a graph of attenuation. How much it gets white when contrast flows in and how much it gets black again when contrast flows out. Not all the not all the volumes in 3D will have a nice graph. So we're using signal processing to actually filter out the ones that have nice graphs. Cool. Moving on, we get to the core CTP calculation, which is math. And believe it or not, when you apply the theory, it actually works. If the data is good, the papers actually are working. There's a series of convolutions and deconvolutions. There's some, if we have electrical engineer fans in the crowd, we can go into it later. but it actually works. And in the end, we want to do some post-processing. What do I mean by post-processing? And I'm getting back to your question about the maps. So we have multiple maps, and each map shows something else. For example, we have a map that shows what we call MTT, mean transit time. How long did it take a contrast to get to a certain point? There's a graph that is showing RCBF, so cerebral blood flow, how much blood was flowing in any point in the brain. The cerebral blood volume, so not the ratio, but the volume. And there's a few parameters here. I'm not going to get into details, but the main maps here are Tmax, mean transit time, cerebral blood volume, and cerebral blood flow. And there's theory behind it that we're not going to get into now. Questions? So the question was if the people that worked on the algorithm were data scientists or doctors. Simplify the question. So both were involved in everything we do. We have clinicians because we need to understand the clinical picture, and we have data scientists that actually perform the job. At the end of the day, it was data science that made it. They just studied a lot of clinical background and had help from clinicians, but it's a combination. So go ahead. Amazing question. Amazing question. The question was, how do you judge if you made a good job? How do you measure the success of CT Perfusion? One of the challenges, we didn't cover it today, but the main challenge, one of the main challenges with CT Perfusion is there's very little ground truth. If you want ground truth, if you want to really know how much brain is dead, you need to take the person and perform an MRI, because on MRI you can see the actual infarct, the actual dead brain. Very few patients in the world get an MRI in parallel to their CT perfusion. So it's very hard to validate, and it's a great question. We validate it by looking at the raw data, by looking at the patient, by looking at clinical picture, by looking at post-operation MRI, but it's not a trivial task. It's a great question. In Viz? So the question was, how many data scientists do we have? Our AI group now has 2 teams with 7 data scientists each and a few data managers, and we have a big clinical annotation team, so around 20. I mean, you can call the titles whatever you like. I'm not going to get into titles today. Deep learning engineers, deep learning developers, algorithm engineers. I mean, I'm not going to go into titles, but yes, we do a lot of things. We have people that are experts on deep learning, and that's where they come from. We have people that are experts in signal processing. We have people that are experts in machine learning. But in the end of the day, and maybe that's coming back to the key message that I want to convey here, we use multiple things. Every problem is different. Even in this one product, it's not simple, but one product, every step of the way is a different problem. Every different problem have a different metric. Every different problem should be modeled differently. And there's a lot of methods that one can apply. We just find the right thing, the right tool for the right job. And that's, I think, the key here. So you take in a great segue to a couple of takeaways, and kind of taking a step back and thinking about what we've discussed in the past 20 minutes at least. So number 1, break complicated business problems to small, well-defined engineering problems. It's not a product manager's mantra. If you want to be able to solve complicated problems, generally in life, but business problems are usually more complex than a yes/no questions. There are end-to-end pipelines out there that solve complicated problems, but at the end of the day, most problems have multiple steps to it, And if you understand what's the metric or what you're trying to achieve in each step, then you can optimize for the metric. Takes me to the second point here, is that for each stage or each problem, you need to find the right framework and then choose the right tools. What do I mean by the right framework? If we have a problem of segmenting ventricles, it's a segmentation problem. Okay, it can be solved in many ways. And depending on the business context or on the context of the problem, you need to choose the right tools. Okay, if we want to be a bit crude, or if we have little data, it can do signal processing. If we have high data variability and we see that putting a threshold is not enough, then we use deep learning at this point. So there's a lot of tools, and the key to being a good data scientist to actually know how to define the problem and then know how to choose the right tool. The tools today are abundant. They're easy to use mostly. Computing power is not a limitation mostly. There's a lot of things you can do. You need to know how to do the right thing. And if you know how to choose the tools to the right job, then you're going to be good at your job. Thanks. Any last question, perhaps from a couple of questions from Zoom? Okay. Okay, so we're actually in time. Any last questions here? Thank you. I'm going to stick around here if anybody wants to chat and have some further question. But thank you so much for the time, and thanks for listening and participating and making this an interactive experience. And Shabbat Shalom.